Good morning, everyone. I hope you can hear me well. Welcome to Big Data Plus, our second to last lecture on this course. So, today we are going to cover two topics related to big data. First is how big data is implemented in cloud, certain elements, certain things that you need to pay attention to when it comes to implementing big data in cloud, and then we're going to discuss about the performance of big data systems. So two shorter topics than the previous ones that we discussed. So let's start with that. So when it comes to big data in cloud, we're talking again. I mentioned this in data storage and management, but when we are talking about cloud, we simply mean a server that exists remotely and that is owned usually by someone else. That we are accessing certain services that were usually set up by a third party, not us directly. So if we use the term our server, right? That's a server that we set up, that's in our ownership, that we have, OS level access to, that we can adjust. When it comes to cloud servers, we usually don't have OS level access. In some cases, there can be OS level access, but usually what we mean is we are accessing them in terms of certain services that exist. Uh, so what does cloud storage allow us? Usually when we use the term cloud storage, it means that that data is stored on remote servers and we can access it over the internet. The simplest example you can think of is something like Google Drive or Dropbox Mega Storage, something like that. When we combine that with big data, as I mentioned, big data is, we're talking about extreme amounts of structured or unstructured or semi-structured data that's generated very, very quickly. So for example, big data, the Google Drive, in the term that you are used to using it, isn't probably the best way of storing, something that's continuously generated or has an extreme amounts of data, because it's limited in bandwidth and speed, and you couldn't really store big data stuff using something like Google Drive. So there are specific services that allow you to scale, right, as your data scales, and allow you certain flexibility, because you won't always have the same amount of data, and you won't always want to save it in the same way. So we will discuss some cloud platforms such as AWS by Amazon, Google Cloud, and Microsoft Azure, some services that exist, and so on, focusing specifically on big data. So, what are the benefits? Let's repeat. I mentioned, I talked about cloud storage, but there are certain benefits to cloud storage itself when it comes to big data. So let's just repeat them. First is scalability. If you have a server, if you fill out all the storage that you have on your server, you have to either clone it to bigger drives or buy another server or something like that. It's a whole process, right? With using cloud storage, you're using someone else's servers. There are probably a ton of those servers, and you can just expand, use a bit more storage. You can think of this again if you have something like Google Drive. If you run out of space, you can purchase a bigger tier of usage. The difference is that scaling is done automatically, right? When we're talking about cloud storage for big data, it's done automatically, and it's done in much smaller increments than you getting, like, I don't know, 15 gigabytes for free, and then getting 100 gigabytes if you pay $20. You're usually paying, per gigabyte or per 10 gigabytes or something like that. And you're usually paying a couple of cents because we're talking about massive storage, right? The second is, cost efficiency. It's pay as you go. You don't have to buy storage in advance, as you can scale it up as you go forward. Flexibility again exists. High availability is something that's very, very key. So it's high availability in terms of both where you can access it from and when you can access from. Again, people are taking care of, if I have my storage server here, because some stuff that I work with, especially medical stuff. Medical data I can share publicly, so I have my own storage server here, and there were a lot of cases where I simply wasn't able to access it, right? Maybe the power goes down in the entire building longer than my UPS can hold, so the server restarts. Our AC died, so the server overheated and shut it down to prevent damage. Internet goes out for the entire building. I can't access it. Right? It's people who work in our computer center reconfigured the network, and I couldn't access it via my VPN. So that there are a lot of cases where if when you talk about cloud, that kind of stuff won't be. Just I see question asked about the link. I have emailed you this lecture. I'm not sharing. So for any of my lectures here, it's all inclusive. So if you have the lecture from that I shared previously, that's the entire lecture. Just as you can see down here, slide 101. But I will share it again just so you have it. Let me just find it. There you go. There you go. So in case you need it, I have shared the file in the chat, and that's it's going to be used for our next lecture as well. Okay, so where was I? Yes, so high availability, it's going to be available all the time. Something like Google Drive going down, you can think about how often that happens. It's extremely rare. And again, collaboration, similar to high availability, collaboration, when you have something on the cloud, due to safety reasons, I can't let anyone connect to my server here, but it can be much easier to set up stuff because they need to connect to the local network, right, of my institution, and my institution may not allow that. For example, in the same way you can't download videos that we have here, right, on Microsoft Teams because of certain policies that my university has. You you might not be able to access my server here. But when we're using cloud storage, right, it's much easier. It's outside our organization, so we can allow more stuff to happen to more people. We can be a bit more lax when it comes to connecting because we aren't thinking about protecting our entire network infrastructure and every computer connected to it. We're thinking only about protecting our data, right? And depending on the data, that can be less critical than protecting our entire structure. So when we're talking about cloud storage, we're talking about either object storage. That's great for so each object you can think about objects as files. It doesn't have to be a file, right? It can be a collection of files. But the simplest way to think about it is like you have a single file with metadata, right? With some information about it. So you have a video, and you have information about who took it, which equipment they used, when it was taken, and so on. That's object storage, right? Block storage is, if you remember from data storage and management, when we talk about storing files, essentially how files are stored on your computer. They're stored block by block. There are some benefits to this, mainly low latency and ease of access, right? Because you're accessing block by block of data, it's much faster to do that than access a whole object. Again, we discussed that in data storage and management. And then we have, I said, object storage isn't necessarily file storage, because file storage is a specific thing that is, data that is stored as you're used to on your computer. That's something like that looks like file storage. Is storing, you have files, you have folders, you can organize them. That's the main difference between object storage, which is just stored. You can imagine it as all being stored in one folder on your C drive, like you don't have any folders and you can just search it by metadata, as opposed to file storage, which you have like a file directories with trees and all of that. Hybrid cloud is a combination of the storage you have locally, right, with the storage that stored in cloud. So usually, if you, for example, prefer having your own server, great, but you are also going to have a cloud storage connected to it, for example, for maybe data that you don't access so often, so you can put it in some like cold storage, or maybe you just want to have it available in case you get more data than you expected, and that and you essentially overflows the data that you have. Cloud storage can connect it, can upload it there, and we talked about distributed storage, where you want to have storage exist across different multiple locations, whether it's for speed efficiency, whether it's for reliability. Again, we discussed that in our older lecture. That's something you can easily achieve with cloud storage. So what the other benefits that you can do, usually when you're getting a cloud storage platform, you usually get other features with it. You usually get stuff like analytics, whether it's something like AWS Redshift, BigQuery, Azure Synapse. Those are some tools that you can use to run analytics. But you also have different setups, for example, for sending them data lakes, distributed computing, or real-time processing. What is the benefit of this? Essentially, it means that if you are already going for the cloud storage, you're already paying for that, you can very easily integrate stuff like analytics or real-time processing of stuff, because the same provider who is giving you data storage is giving you services for whatever you may need, right? So if you're choosing where to store your data, and you know that you need real-time processing, you're going to check what does Amazon offer, what does Google offer, what does Microsoft, IBM, what are their offerings, and you're going to pick based on that and select, whether you want to go with certain cloud provider based on that. But that's one of the greatest benefits, because if you're using your own server, you want to get some analytics software on it, you need to pay separately for that software, you need to install it, you need to manage it, and so on. And you can run into problems. So like later on, you want to integrate real-time processing, and you realize that the software you purchased for your real-time processing doesn't work with your big data analytics software. They just don't play well together. They might crash each other or something like that. That's a possible issue. If you're going with Amazon, you get S3 for storage. You can it's guaranteed that if you want to combine Redshift and Kinesis, it's going to work together, because they were designed to work together from the top down. Another benefit, is just generally when you have a big provider like Amazon, they have full teams that are dedicated to security. They have full teams that are dedicated to compliance. As we talked about compliance and stuff, I mentioned it's best if you have a person in your company that's just in charge of that, because compliance rules change. Laws changes, like the same reason why people working in your accounting aren't just adding numbers and that they are following laws that, so they can know how to book certain things, how to render certain payments, etc., right? To make sure everything is legal, all the taxes are paid, and so on. Those stuff changes, and they need to keep up with it and be informed continuously, right? Same goes for compliance and security. And the reality is that a lot of teams simply aren't capable of having someone supporting them in that way, right? Where you have two people who are essentially doing nothing but making sure that what you set up initially is fine, and maybe doing some updates every couple of months or once a year to make sure everything is up to date and your protocols are up to date. Your access control and stuff, compliance with like GDPR and stuff is okay. That's a waste of money, right? Because you're paying, I don't know, in Croatia, you're probably paying something like 40,000 euros you're spending on that person, or more, depending if they're like a security expert or something. So based on that, you can have spending like 100,000 euros just to get someone to make sure you're in compliance and your security standards are up to date. It can be a problem. What they're doing. So some people will pay for an outside company. Again, they're probably going to charge you a lot because they know that you will be spending. If they know you're going to be spending 40,000 to hire a person, they might charge you 20,000 euros to hire a person, right? With something like cloud, right? If you're using a cloud service, that is essentially baked into the cost, and it's so cheap because they are making sure that everything is the way your data is stored on their servers is in compliance with GDPR and so on. Because it has to be, because they're going to get fined a lot. Even if it isn't, it's not going to be your fault because if there is a data leak based on AWS, based on the infrastructure, that's Amazon's fault. It's not your fault. If it's a fault of obviously your application or something, if you made a genuine mistake, then it's your fault. It doesn't prevent it. That it doesn't mean you should not care about security or compliance, but there are elements of it, such as access control, firewalls, hardware level encryption that you simply don't have to worry about, and it helps to take care of it. You still need to worry about security and compliance at a level of your application that you're developing, and so on. So there are a lot of, when we talk about future trends, a lot of this is stuff that I can't really predict the future, but yeah, talking about stuff that is being worked on now. This won't necessarily function in the future. Won't necessarily be the true, but I just like mentioning it because this course is meant to educate you in general. So I like giving you an idea, especially if you are more computer engineering or computer science focused, that you can get some information about what's going on, what are people currently working on. One stuff is edge computing. What does edge computing mean? It means that data is processed closer to where it's gathered. So this means that if for example, I care about certain sales, how many sales each of my stores had, and I have 100 stores. Instead of each of those stores sending me all of their sales, so it could be like a gigabyte of data from each store, and me getting 100 gigabytes of data that I need to process. They are going to just so I could figure out how many sales in total were per each store. That's nonsense because they can just send me their total, right? So they can calculate their total data locally, on their edge node. Edge node simply means a computer they have locally, whether it's a server everyone's connecting to or like a central workstation or something like that. It depends on the use. It can be something like a Raspberry Pi or like a small computer like that. That's collecting data and immediately processing it, and that and the key data that I actually want to know, which is like the amount of sales, is being sent to me in total. Usually, this means you will have a server. All the raw data is getting stored locally for at least a couple of months or something in case we need it, and the key data that we want to know is going to be sent back to us, right? Now, the problem with this is obviously we don't have all data, we don't have all the information, we might not be able to do some analysis, but essentially we are getting the key analysis that we want without using a ton of bandwidth and sending a ton of data every day to our central servers. Another is serverless computing. Again, this is a term that computer scientists coined. It's not serverless computing. There is always a server, there is always a computer. It just means that from your perspective, a server doesn't exist. From you as a user, you don't have to worry at all about the resources. This is similar to essentially cloud. Where I said you don't have OS level access, you don't need to run updates, you don't need to run anything. Today, you still need to, even when you're using cloud, you need to do some OS level things, some accessing. You may need to fire up a terminal or something, but lowering the amount of times you need to use anything that's not a nice graphical interface, that's the point of serverless computing, where you can use data, you can run analytics, you can check the data, you can see what's going on without the need to hack into the mainframe, open the terminal, and type in commands and stuff like that. You have a nice hardware, a nice graphical interface that abstracts the hardware. What is the benefit of this? Well, it requires less training. It's simpler, it's clearer how to use. You don't need to memorize, 100 different commands to navigate the system and so on, because everything is, one click away. AI, we talked about, this whole course focuses on artificial intelligence. That's what we have here as well. Integrating AI, especially on cloud, is super simple, because you can, with relative ease, add stuff in there, relatively easily. Just add information and follow up on possible changes, directly model stuff and stuff like that, because as I said, as I talked before about the different services, and it's really easy to integrate a service, you can really easily integrate AI. So that's something that's being worked on. Quantum computing is something that's being worked on also for a lot of time. I won't go into depth about it, but it's something that could be very, very useful when it comes to performing stuff like MapReduce algorithms and stuff like that. And again, a lot of focus, especially lately, is being given to data privacy. When the internet started, we had this idea like no one really cared about privacy. We posted our, a lot of information is shared. We didn't really care about it in detail that much. Today, that is changing, and more people, are privacy conscious. They want to understand and know what happens to their data. So that's something that is moving forward. We are trying to make sure that any data that we collect or any data that exists is actually being stored and used in a way that protects privacy. So as I mentioned, serverless architecture for big data, you have essentially an abstraction of the underlying infrastructure that will allow you as a developer, you don't have to worry about how many cores you have, how many data you have, what kind of hardware you're connecting to. You basically have an API, an application interface that you can connect to, and you can run stuff. Everything about the server, the hardware is taken care of in the background, right? So it's not serverless in the sense that there is no server. A server doesn't exist. Server very much exists, but from your perspective as a client, as a developer, you don't have to worry about it, right? It simplifies everything to you, because you just need to worry about development. There are services. AWS Lambda is by far the most popular, and there is also Google Cloud Functions and Azure Functions that allow you to run stuff. It's great for big data because it's much easier to get to train. Some people can get scared a bit when when you tell them like, oh, here's what you need to do. Here is, let me use an example. If I'm, is it going to let me connect? Yes. If I'm telling you like, oh, you need to download the information from here, and you have some information here that you need to download and so on from a server like this, you're going to need to type in something like SFTP, and then my IP address here, the location here, then IP, then the path, and so on. That's pretty complicated, to type in, and everything. People are going to get confused if you start telling them to type in something like this, and they will forget. They will try to write it down. They will write it down wrongly. It's much easier for me to tell them something like, "Hey, here you can just drag and drop and download data." Something like this is much easier to do. And that's basically when we're aiming about talking about serverless architecture. The client doesn't see this. They don't see like a ton of comments, etc., and errors, and this metrics like terminal. They see a nice drag and drop file, despite the fact that when I do this, when I drop and follow something, just the same command that I would type in here executes in the background. So that's the idea behind serverless computing, and that abstraction of serverless computing, especially when we're talking about people who are analysts, people who are not computer engineers, right? No matter what field they are much more relaxed usually when you give them something that they can click on and drag and drop. So again, there are some benefits that are listed here. These are mostly from the perspective of me, from the developer's perspective. First is scalability, because you aren't writing the code that's specific to a certain architecture. You aren't assuming a certain architecture. You can easily scale it up to higher, move it to a more powerful computer, and so on. Again, cost efficiency, as always, you have that pay-per-use pricing. You are only paying for the computing power, CPU time that you use, right? And then you have some specific stuff like reduced operational overhead. You have less stuff to worry about in the background, managing servers and so on. And it's faster time to market because you already have tools ready for you. You don't have to worry about setting up servers and so on. And again, real-time data processing here. This is something that's used a lot in real-time processing because it's much faster for you to set up. So what does this, when we're talking about serverless big data, what are the key components of it? You have compute functions, right? I mentioned AWS Lambda, where you are actually getting the information, with the calculations done. You have databases that are stored serverlessly. Again, this means that essentially you don't see the server behind. You just have a database you are accessing through some sort of a platform, and same goes for setting up data streaming or data pipelines. Data pipelines are basically, I explained them last time, when you have a source of data, you have the target where you want to collect the data, and in between you have some processes happening, maybe transforming that data, maybe analyzing, running some basic analysis, and so on. Generating metadata, for example, is very common. So where is serverless architecture used? A lot today, real-time analytics, ETL. Basically, I talked about it a lot. Extract, transform, load for building, scalable event-driven elements. Why is this mentioned event-driven? Because when you have a serverless setup, it can exist somewhere virtually, right? You don't need to have a whole server in your house dedicated to running ETLs or to setting up real-time analytics, right? What's the problem with real-time analytics when you have a server that's doing it as opposed to like a serverless architecture? Again, serverless architecture doesn't assume it's scalable. It doesn't assume a certain server, a certain CPU, a certain amount of CPU cores. Like when we go, like for example, when I go here, if I type in this, you can see that this has like 20 cores, certain RAM and stuff. The real, when we're talking about serverless, if we need more, we'll simply get more. Our current processor isn't fast enough to process the data that we are receiving in real time. Great, let's just run, let's just expand it to get a more powerful server. and that's essentially the main benefit, also for ETL. It's scalable. We can more easily adjust it. Same goes for machine learning, and same goes for stream processing. We can much more easily adjust and scale up things because we aren't focusing on writing on a specific server. We are writing it somewhere abstractly. And what happens in the background is that the services that we talked about are going to automatically expand. So we aren't creating a database and thinking, okay, we can store 10,000 entries here because that's the space that we have. No, we are just creating a database, and it's going to these services are going to automatically allocate more spaces, more actual hard drive space, right? So we are moving towards the abstraction. Obviously, there are some issues. If we have a hardware level error, right? It's much harder to debug that because you don't have hardware access. You can see what's going on, what went wrong. So that can be a problem because you're abstracting that layer and have access to it. The other problem is no cold starts. If, as I said, when you're accessing your Lambda function or something, you're still accessing a server somewhere. And if you have your own server, the server is live, it's running. Yeah, here's my server. It exists. My Lambda server doesn't exist currently, and I need to. It exists somewhere in some storage, and it needs to actually be put on the server, so you can have that cold start that takes a bit of a time, especially if you haven't accessed it for a while, and the people at Amazon have moved it further, back into colder storage. That takes a longer time to load. And again, you have certain limitations, on execution time. Memories are running like very complex, like supercomputer level tasks can be problematic because they simply aren't designed for this, and they might disconnect you or something like that because they're designed for much simpler tasks. Again, I mentioned scalability, so for the end here, near the end of this topic, I wanted to more strictly define it, but basically, just so we understand it, again, I've used it a lot. You should understand it by now, but scalability refers to the ability of a system, network, process, whatever we're doing to handle increasing amounts of work or data, right? So think of it this way, if you have a scalable process, for example, let's say scalability isn't just a big data term, it's a general business term. You have probably heard of the term scalability if you're in business. Is how well can your business scale? That's a problem, for example, with manufacturing. If you're manufacturing something, it can scale easily. If you get a demand, if someone tells you something like, hey, I like your product. I want 10,000 of it by the next week so I can put it on my shelves and sell it. In manufacturing, it will be a problem. If you have a machine, it's going to be less of a problem, and so on. Like scalability is how fast you can adapt to the system in case you grow the data set, right? So the difference between right now I'm selling my product on Etsy. I see it's very popular, and I get maybe 10 sales a month. Now I'm going to publish it on Amazon. I'm going to publish the same product on Amazon, eBay, Alibaba, whatever, and I suddenly get thousands of sales a month. How well can my system handle that? We have horizontal scalability, which means basically let's add more machines, right? One server isn't enough, let's add another server. And vertical scalability, where we have the existing hardware, we're going to upgrade it. More powerful CPU, more or faster random access memory, and so on. To call the system scalable, it has to be have high availability and performance, regardless of not regardless, but as the data volume, variety, and velocity, how fast data is generated, how different the data is, and how much of the data is there. As it grows, it should keep the same performance, the same availability, shouldn't crash. And this should be as reliable, as before. So what is the problem with the scalability? Actually, there are with big data get very rapid increases. That's something that's also I haven't mentioned specifically. I talk about high velocity, high variety, but the problem is that you don't necessarily have a linear, increase as you might be expecting. Is the increase tends to be exponential. Like if your platform gets popular, and if your platform, like I don't know, TikTok, you had 10 users today, you will you might get 15 tomorrow, 20 tomorrow. But if you hit like actual popularity, right, like it goes viral, essentially the growth is exponential, and you won't go from 10 to 15 users, you will go from 10 to 1,000 users, and from more realistically we'll go from a few thousand users to a few million users in terms of days, right? So maybe in terms of months or something like that. Uh, so actually managing that's a big problem. Then the problem is real-time processing, as I mentioned. We talked about how real-time processing is done and so on, and finally cost constraints. Can you scale up infrastructure? Yes, but you can't infinitely upgrade stuff. You can't infinitely add more machines. Especially, with horizontal scalability, it's a problem because you get increases. Like my computer now isn't enough. I want to get multiple computers. Okay, I can get maybe 2 computers in my office, but 3, 4 more. I'm okay. Now I need a data room. I need AC to cool it. I need to buy a rack where I'm going to store my machines. Okay, I fill up the server rack, right? The server rack, if you aren't familiar with the term, if you aren't a computer scientist, I'm simply talking about a rack, something like this, where you store, servers. Uh, as you can see here, you have multiple servers stored. Okay, you fill up one of these. Oh, you need to buy another rack and everything that goes with it. That rack doesn't fit in your server room. You need a bigger room. You need more cooling. Horizontal scalability is very expensive. Vertical scalability can also be expensive, but it's also limited, right? Because if you're getting, would you rather have two? If you have like someone is doing physical labor for you, would you rather have 10 people or one really strong person? If you're talking, would you rather have 2 people or one really strong person? That can be discussed. But if you're talking about whether you have 10 or 20 people compared to one really strong person, well, you would rather have 10 to 20 people. So horizontal scalability is generally preferred today. As I mentioned, there are limits, and the more you're splitting, the more you're distributing your system. If you're talking about different computers doing the same task in the same geographical space, like in the same room, that's much less complex than having two uh, two server rooms with 20 computers each, 20 servers each trying to do a certain thing. With these two data rooms being separated, right? You are introducing complexity by increasing your distribution, and again, dynamic workloads, right? This is why that flexibility that we talk about, like flexible scaling, is super important, because you can't predict workloads, and you don't know how workloads are going to increase. There is certain predictability. If you have like a video game and you're having a big update, you're probably going to have like a peak of players or something. Okay, but sometimes you have completely random stuff, because let's go with that example of a video game. You have a video game server. Each time you have like an update, added content, you're going to have a peak of players. You get more players. That's great. You can predict that. Each players are playing. Uh, you know, uh, most of your people who are playing are in Europe, so you're going to predict, okay, in Europe we are going to have a peak around when people come home from school, around 3 or 4, they're going to play, so we're going to get more. We can predict that, great. Then can you predict stuff like COVID? A lot of people were at home. COVID was famous for being like extremely problematic for scalable environments because services like Netflix or YouTube were under such pressure because so many more people were actively using them than before, uh, because they weren't expecting it, right? If you're talking about a video game, what if like a popular YouTuber, plays your video game and now you get sudden increase in popularity, right? Because people have seen someone play it. Yeah, so those are elements that you can predict and they can cause you a lot of trouble if you don't have like a nicely scalable environment, or in other words, elastic scaling, where you use cloud services. Again, serverless architecture. You don't care what's in the background. You just get more resources as you need them, right? Again, we talked about partitioning data, splitting it, distributing it to get easier workloads, easier to process on different systems. And we talked about caching, where essentially caching means that you are storing the data to be processed on the server as you will as you want to reduce the time, right? So you're storing it geographically on the same server, right, where it's going to be processed, just so you don't wait so normally if you have a server and you're processing some data, server processes the data and then puts in the request, send me the next chunk of data, and you send it the next chunk of data. So we get that like 1-2 step, like you get process, request, receive. Instead of doing that, you know what the next data is going to be processed. So while the processing is happening, you are already sending it the next chunk of data to process. So as soon as this machine is done, it can send you the information like, hey, I'm done, but it doesn't need to wait for that message to reach you and for you to send the data back. It just automatically gets that data. Sent to it, or it's automatically, the data has already been sent and it's waiting for it, so it can automatically go and process the next chunk of data. And while it's doing that, you are going to send it the following chunk of data and so on. The other issues are load balancing. Basically, you want to distribute tasks evenly across servers, so you don't have one server who is killing itself, trying to process everything. Yes, it might be slower to, if you have 2 servers, if you have a server in Croatia and we get a lot of connections, it might be beneficial for me to transfer some users to a server in Germany. It's going to be slower for them to access, but it's not going to damage. By damage, I mean like crash the server that I have in Croatia. And then you have automation and orchestration, where you just automatically set everything up. And finally, you want to monitor and optimize stuff to see what's going on, what are the scalability issues, etc. Did the server came close to running out of memory? What happened? What was the cause of it? And so on. Okay, so I talked a bit about performance and stuff like that. We're going to focus a bit more on the actual performance of big data systems here. Again, we want to go into crazy in depth. This isn't that sort of class where we like really go into programming and complexity and so on. This is more like overall introduction, so we're just going to discuss it on a certain high level. What does it mean when we talk about performance tuning, and what are certain adjustments we can do to performance tune big data systems? So when we're talking about performance tuning in general, that means optimizing the systems that we have in place to scale, to handle large amounts and high velocity amounts of data. We want to reduce bottlenecks. Bottleneck is anything that slows our data down, our data processing speed. So as I said, if you have a pipeline where this is the source and this is the output where we want it, like we want to store it on hard disk on the server somewhere. Every step that we take in between, that's all together a pipeline. If we have something that's very slow, like a very slow processing step here, that's where we want to address it and we want to raise the speed of it. So we have a constant throughput and we get like a nice flow from the data being generated to data actually being stored and ready to process. We can address that at infrastructure level, at the data architecture level, how data is organized, how queries are performed, and how our processing frameworks, programs that we use. When we talk about processing framework, we mean a program that we use to process data. If you open your data in Excel and run analysis, that is a processing framework. Don't be afraid of, seeing a name that you're like a framework that you're unfamiliar with. It's just a program, right? It's a fancy word for program. Again, if you are a computer science, computer engineer, I am simplifying. I know that the framework and Microsoft Excel isn't the same. I'm just, using that as an illustration. So what are the main issues that will cause you trouble? First is data volume, how much data is there, and the data velocity. We already talked about these two at length in this class. I told you there's a lot of data and the data arrives to you fast. Okay, we talked about that a lot. We don't need to repeat these elements here. The other problems that are a bit more specific are resource contention. Basically, if I need to access, this is more like computer engineering, but basically your compute, when you run a program, it's going to try to access certain resources. It's going to try to access CPU because it needs to calculate something. It's going to try to access memory because it needs to read something or store something. And same goes for disk, right? Memory here means random access memory, RAM, right? This is why you have multiple CPUs, and even if like your application isn't written, like you talked about, if you are in introduction to HPC class, you talk about parallelization. Even if it's not parallelized, the application itself, when we request a CPU, if we have multiple CPU cores, or sometimes core is more of a marketing term. The term you will hear computer scientists uses multiple CPUs. That doesn't mean multiple physical CPUs. It means you have multiple processing units or multiple cores, threads, whatever you want to call it. So this means that you are accessing it. For example, one way of solving resource contention, if you have two pieces of software, two programs trying to access CPU, is having multiple CPUs so they can access it immediately and get the response, get the calculation done. Right. System latency is basically how are you going to reduce response times, right? From the time when I put a request and say, hey, I want to see how many sales there were in a certain store. I hit enter, but the time the information gets back to me, that is response time query, right? And essentially how to scale well without actually degrading performance, because as I said, adding complexity, adding distribution can actually lead to additional issues if you aren't paying attention, if you aren't doing stuff properly. So how can we optimize infrastructure? First things first, we can do hardware tuning. We can choose appropriate CPUs, right? So again, as I said, somewhere around here, we want to maximize performance while minimizing costs. We can just go like, oh, let's pick the fastest possible CPU. No, we want to pick the CPU that's appropriate to the system that we're using it in. One example is you have, for example, Intel Xeon server CPUs. You used to at least have like platinum, gold, silver. And a lot of people would immediately go like, oh, let's get the platinum one. And when I was consulting and stuff for hardware, like, oh, we can afford the platinum. I was like, no, the only difference between silver, gold, and platinum is how many physical CPUs you can have in a single system. Like silver will allow you to have one, like you have in your normal computer. Gold will allow you to have two, and platinum will allow you to have four or more. Right? That's the only difference. For your application, you can get the silver because you're running a single server CPU, and it's going to cost you much less, and you'll actually get higher performance than you would for the platinum of the same cost or even higher cost, right? Same goes, some stuff you want to upgrade, SSDs, you want to get as fast as possible as you can afford and so on. But just want to illustrate there is more to this than just buy the most expensive you can. For example, that's more workstation level than like HPC and big data and cloud level. But for example, getting an AMD CPU with an AMD GPU may allow you to gather certain benefits from one or the other because they can use, for example, there was, I don't know if it's still relevant, but there was technology that allowed you to use system and memory if you had both AMD CPU and GPU that allowed you to use system memory for the GPU processing and so on. Second is how are you going to organize your cluster? How are you going to configure it? How many nodes are you going to have? Because each node, I said that a node can be a computer. It doesn't have to be. One computer can be multiple nodes, right? For example, and what are the role is going to be? Not every node doesn't necessarily have to be the same. You could have a storage node or you can have a CPU node. If you're getting, if you already have some nodes and you're getting like a really powerful CPU to be your storage nodes, instead of them being processing nodes, you're making a mistake. Those are simple examples, right? How is the network optimized? Are you having any beneficials in your network? Is there any like you have a really fancy network, but then it's connected to a $10 router that's falling apart because it can't process the amount of data you're trying to push through it. That's something that you want to have. Then you have a resource allocation. Are you going to when you run the program and that program wants to access certain data, certain amount of CPUs, how is that going to be determined? Are you going to use something like Yarn or Kubernetes to address that, to basically figure it out for the computer, which resources are necessary for it? And finally, you have elastic scaling. Basically, any auto-scaling features, like if you're using too much memory, access memory on another computer or something like that. Those are the elements of infrastructure optimization. We talked about data partitioning and sharding. I'm just going to repeat it here, in case you don't remember from the last time we discussed. But basically, partitioning is splitting data across multiple nodes. Sharding is splitting elements of data. Yeah. Essentially, we had the whole conversation. If you haven't been here last week, you can check it out online. I won't go into details about what it is. So essentially, you want to make sure to not run into problems if you're running partitioning, if you're running sharding. You want to make sure everything is consistent, and you want to avoid hotspots. That's the key element. Hotspot basically means that if you're processing something, like you're running stuff geographically, right? As I said, like I'm connecting to the server in Croatia because that's the fastest, but I have a lot of people here in Croatia, and all of them are trying to connect to the server. Maybe it's better for me to actually partition that a bit differently and send some people to server in Serbia or in Germany or somewhere else. Yes, it's going to be a bit slower for them, but it was that hotspot that's actually going to slow down the thing for everyone, right? So it's better for half the users to have to wait a second than all the users to wait an hour because the server went down, right? What is when it comes to querying, if we're talking about the database querying, getting information from a database or a data lake or something like that. That's querying is just the general term. Don't necessarily automatically connect it to SQL, right? Standard query language. It's just whenever you have a term, a command that allows you to get data from somewhere, that's query. How you can optimize it? You can have indexes in your databases that basically indexes tell you what is here. For example, I told you your car registration. If you're in European Union or close, or even if you aren't, if you're nearby, you will probably have your country indicated at the start of your table with HR for Croatia, SRB for Serbia, PL for Poland, and so on. That's a type of an index, because now I can, if I'm looking to search through all of my data and I know that I'm looking for an address of someone who lives in Rijeka, I know that I can immediately, I don't need to check the entire data. I can just check whether they are Croatian, and that's just one piece of data that I need to check. Is much faster than checking if they are Croatian and checking whether it's the table that belongs to Rijeka or not. Right? I can just use the index that country to just check yes or no for faster searching. Caching, as I mentioned, is storing frequently. If you have a data that you frequently access, you store it on the server that you're accessing it to, so you don't need to get it all the time, right, and access it all the time. The views, as I mentioned, the view, if you don't remember from data storage management, the view is just a way of filtering the data and showing the data to your users. If you have stuff that is accessed often and that query, especially if that query is complex, so for example, a lot of people are calculating the average sales per each item you have in a store, and that's something that you do often. You can have this running in the background, right, occasionally. So when I ask for it, if it's not been more than an hour, or if the data hasn't been updated yet, you can just show me the complex query results that was run by you automatically in the background, instead of running it each time I request it. That's very useful, especially if a lot of people are accessing something. Querying how queries are executed, setting them up, managing that, what they're using, which parts of database they're accessing, which data they're accessing where, and essentially combining queries. If you have two queries that are accessing data from a server here, combine them and get the data for both, right? So that's the idea of batching queries. Here are some elements, basically, if this was a full computer science class, we would, have all of these and test them and check how they're working. Again, we are on this more of introductory class, so I just want you to know that for each of these frameworks, whether it's Hadoop, whether it's Spark, Flink, Kafka that we mentioned during this class, each of them you can tune, right, based on what you need. So again, Hadoop, for example, for HDFS, Hadoop distributed file system, you know that you're storing the blocks by default at 128 megabytes, but you know that you aren't going to be storing anything less than 500 megabytes. Increase that block size to 512 megabytes. Replication factor is how often it's that data is replicated across different nodes in the server, in the pool of servers for Hadoop, right, across the nodes. This data doesn't matter to you at all. You just want to have it distributed. Don't replicate it at all, right? You don't need to access it quickly or something. Replicate it once or twice. Don't replicate it 3 times as the default or 10 times because you want to be sure, right? Those are basically the ideas. But what I want to show you here with this slide is essentially for each of these frameworks and any other framework that I mentioned, you can individually tune it to improve performance. And if your performance is low, it could be worth doing and worth observing. Then, when it comes to storage, there are a lot of optimizations that you can do storage-wise. First, it's choosing the right storage type. It says here, HDFS if you're batch processing, you need scalable storage PKS3, you need, if you're talking about hard level, use SSDs instead of HDDs, stuff like that. Data compression techniques, if are great, but they cost CPU, right? If you're paying in CPU time, right? Processing time to compress something, to zip something. It says in Snappy, gzip, tcroll. If you are familiar with FAR or zip, that's essentially it. To reduce storage, to reduce input-output cost. So basically, the bandwidth or the hardware use, hard disk used when you're sending it, that's something that you can do. You can compress data. Of course, it's going to cost you some CPU time. There are file systems that do this automatically without you even noticing, so it can be done quickly, but there is an existing cost to it, right? Computer-wise. You can use specific storage formats to speed it up. You can do data lifecycle management, where you're essentially checking the data and determining, is this data old? Is this data something that we don't really need anymore, that has been accessed in a while? Let's just store it somewhere, in like cold storage where we don't need it, because we are testing it, or just delete it. And finally, just as a note, I never like deleting data automatically, because no matter how carefully you set up rules, you could accidentally delete it. So me personally, I never delete the data. Whenever I'm setting up stuff, I create a folder where I just dump all the data that should be deleted, that my computer, my program believes it should be deleted, and then I send a reminder via email when that gets to a certain size, to be like, hey, check if this data can be deleted, and then I can scroll over it, make sure that nothing important got caught up accidentally, and then delete it manually, right? That's my preference and my advice, because no matter how smart you think you are when you're programming it, you might always overlook something and cause yourself issues. And finally, we have data locality. Where is the data stored? Let's keep it close, because it will, of course, faster processing, because we have less time spent on that information being processed from point A to point B. You want to have monitoring tools. Grafana is very popular, and I personally use Grafana. The problem with Grafana is that it is so fine tuned that you can take some time to set it up, but it's my advice if you have time, if you want to monitor anything, even if you are in business or medicine and you want to monitor stuff, not connected to CPUs and computers, stuff like that. Check out Grafana. It's really great tool. When we're talking about computers, you want to keep key metrics like CPU, memory, disk IO. There are a lot of tools out there that exist for monitoring this type of stuff. I am going to actually show you some. For example, this is Glances. I connected to the wrong server, but essentially this can show you, these are the servers. This is stuff that is running on my server. I connect to wrong server, otherwise it can show you the GPUs as well. I just not the wrong server, but the wrong user that does have permission to check it. Through this, we have CPU, memory, what is the load on it. I can monitor the network here. There are other tools. For example, we can do something like HTOP is very popular. You can see CPU by CPU basis. Like for example, this is a B server with 96 CPU cores. Or you can you can have more specific tools like NVIDIA SMI for GPU monitoring. We can see that nothing is really running now. Yeah, so those are some basic monitoring tools that you want to monitor on any computers, like CPU usage on your computer. I'm assuming most of you are on Windows, you can go here. So Control Shift Escape opens your task manager, and then you can go here and you can check your current CPU, disk drive, Ethernet, even your GPUs, like what the usage is. And you want to monitor this, especially when you're running something, to make sure you aren't running into any sort of problems. And then you can use that to identify any bottlenecks or anything like that. So for example, here you can see that my memory, even though I'm not doing anything really serious, is around 16 gigabytes. So I want to optimize my use. Maybe I want to kill a few Chrome tabs or something that I have open. Otherwise, you can see how it dropped nicely, right? As I, keep killing certain programs that I have open, also just for monitoring and stuff while I'm teaching, you can see that there is a drop in usage, but I'm still using a lot of RAM, which is why, I determined at some point I upgraded myself to 32 gigs of RAM because I needed it. Yeah. Profiling tools are basically just software that will help you determine, what are the errors, what's going on, what are the possible issues that you may be running into, and so on. And will tell you like, hey, you're lacking CPU power for certain usage and so on. Yeah. Okay. Then we have load testing and benchmarking. There are a lot of tools. Basically, what benchmarking runs. What does benchmarking and load testing mean? Load testing is seeing how your computer acts under a certain pressure, right? So it's essentially a stress test, and the difference in just nomenclature between the stress test and load testing is stress test is pushes everything to 100%. Load testing won't necessarily push to 100%. It will just check under certain conditions, like, hey, how does my computer act if 100? If I know that technically my computer supports, I know 100 users working on it, but I know that usually I'm going to have 90 users. Let's test how it behaves under 90. Let's test how it behaves under 100. That's load testing. If my computer is meant to support 100 users and I connect 150 to it to see if it blows up, that's stress testing. That's the difference between the two, if you ever see the terminology, right? Benchmarking is just having a set of tools that they can use from one computer to the other and see if it's behaving as expected. If one system, if I have 10 same systems, I use the same tool to test it, and I get vastly different results. I get one that is, I get this usually get a score, and clearly like a score of this is 900, and then one computer, all are around 900. One computer is at 500. Maybe there's an error, hardware level error. Maybe it's heating isn't properly set up and so on. That's something that you may want to check. Again, load balancing and resource management, I talked about it. Again, load balancing will distribute workloads across multiple nodes. Resource management will allocate compute and storage resources usually on a single server. Again, the idea is just informing you about this term. When we are talking about load balancing means that we want to move some of the CPU use or just the compute use on different servers. Resource management means we are managing resource of an individual server usually. Yeah. Both of them want to be done, by basically to enhance performance, improve tolerance, basically like, I showed you before, I had my memory, I optimized it a bit by shutting off some stuff that I didn't need. The benefit of that is if I open something that's relatively complex, like I open some software or something that is going to increase my memory use, I have much more space now compared to before, and that's the idea of running something like, resource management and improvement. This is key to do in big data, especially when you have like distributed systems, because uneven workloads, whether across multiple nodes or on a single node, can significantly degrade performance, because you can misjudge the current use. For example, here is a possible issue. Let's say you are monitoring the average use across nodes. You have 3 nodes. One node is at 100%, one node is at 100%, and the third node is at 0%. You look at that and mistakenly calculate the average load as 200% divided by 3. You get, so it's 66% or something like that. You say like, oh great, I can push more. You push more usage on it, and the one that had no load on it will handle that new load that you sent it, while this two that had 100% load will fail, right? So that's why you want to properly load or have a resource management system that will take such elements into account. There are some techniques here that you can use. First is round robin, which will distribute tasks evenly in sequential order. It will go from one node, then the other node, then the other node, right? And make sure everyone gets the same amount of tasks depending on the current load of each server. This connection will give it to the one that has least active connections. This is great for servers that use something where everyone is using the same amount of resources, like video games. Everyone is more or less doing the same thing and sending the same amount of data. So it's great to measure by connections, because more or less every user is going to use the same amount of power, compute power, no matter what they're doing. But for something like scientific computation, supercomputation and stuff like that, it's not good, because I can connect and run something that requires 20 servers at 100%, and you can connect with something that's much simpler, just like visualizing some graphs or something. So this is great in some cases and not great in other cases. You can weight distribution stuff by weight, where you know which tasks exist, and you can give them certain values and say which is more complex, which is less complex, and then distribute based on that. You can have, and then these are two just techniques where you want to mention that you want to have consistent hashing that basically notes which each tasks, any data is, if you have a certain task noted, identified with a certain value, you want to make sure that's consistent. You don't have multiple values on multiple servers, so you're making mistakes and sending stuff to a wrong node, and you need to rebalance it because you miscalculated, because you didn't properly identify the tasks on the server. And finally, something like dynamic balancing, where you want to automatically adjust stuff. You don't want to do it in advance, or occasionally you just do it as it happens. You will move tasks between servers. What are some resource management strategies that I just want to mention is resource scheduling. That will dynamically allocate resources based on essentially priority and demand. Can I satisfy your demand if I'm requesting 10 computer nodes, and they have them? I will give them to you. If not, you'll wait. And then also priority. If another task with higher priority that requires the same amount of power comes, is going to prefer that. Another management is resource isolation, where you use something that's called containers, which is essentially like a virtual computer, virtual machine that runs a single workload, and that's going to exist for that single workload. You have quota management and auto scaling, and as well, I mentioned Elastic. Elastic is something that's mentioned a lot, where you want to, you have resource pools, across nodes, then you have a pool of 3 computers with that you can address together and share data between. What are some tools that exist? Again, just to briefly mention them, Apache Zookeeper. Again, I think I mentioned, but you have a lot of tools in Apache. Hadoop are named after animals. You have like Hive for bees. You have a pig. You have the Hadoop logo is an elephant, if I'm not mistaken. So you have they the Hadoop logo is an elephant. Right, then you have like a hive, which is reminiscent of like stuff with a lot of the services are named after animals, look like an animal. So you have the zookeeper to balance them, a bit of a joke, right? Then you have some additional load balancers like Nginx is something you may encounter if a website fails somewhere. You might get an Nginx error. Let me see if I can force one to happen. No, I knew a website that would fail if you try to load it in a certain way, but it appears they fixed it. So no demonstration, but basically you may see this if a website doesn't work, if it wasn't configured properly, you might try to load it and find something like welcome to Nginx. So that's why I just mentioned it here. It's a load balancer across different servers when you're connecting to a website. Again, there are cluster managers for, when you have multiple nodes. As I said, you want to monitor, you want to check what's going on, whether you're using Prometheus or Grafana. As I mentioned, I'm very particular on Grafana. It's a really, really great open source tool. And again, you have cloud platforms, which is, as I mentioned today, serverless environment where you don't care about load balancing yourself. Someone took care of it for you, and the load balancing is done in the background. You don't worry about any of this. What are some best practices for just continuous optimization? Make sure your software is updated, whether it's your operating systems, whether it's your frameworks. Make sure everything is as up to date as possible without breaking your environment. Whenever you change something, document what you done, what was watching. And something that I've noticed a lot of documentation are doing is that people start documenting, but they don't note what they changed it from. And then what happens is that value is 0. Someone changes it to 0.5. Right, and when I say change it to 0.5, that usually means they open like a text file on a server and change something, right? That's how it's usually done. Then they delete 0 and the 0.5. They don't update it, but the server works great. Then someone opens that file. They go from 0.5 to 1, and they document it. They say like we changed it to 1, and then a day later, to test whether that's going to help with performance. The day later, they realized everything is falling apart, and they changed it to the last documented value, which was 0. Nothing is working again because someone didn't document that they changed it to 0.5 in between. So whenever you are documenting any tuning changes, anything, note we have changed the value from this to this, to avoid any mistakes, to avoid any confusion. Right? Don't just document what you change it to, because the person before you didn't document, you will actually lose that information. So just as someone who ran into a lot of problems because of this kind of stuff, always note what you changed it from. Collaborations between teams. This is a nice point. In reality, it won't happen. Just speaking from experience, you can tell developers how to use something. They will do whatever is the simplest for them. You can tell database administrators, but they just care about the database performing nicely. They don't care about queries causing issues and so on. So this is a nice thing. This would be a great thing to achieve, but usually in my experience, you won't get it. Again, periodic audits. This means run those benchmarks on individual parts of your system. See if something is something was there a benchmark that significantly dropped? Okay, let's check from the last time we ran the benchmark. Let's see which changes were documented. Let's try to see if we can adjust something here. What changed? What caused this performance to drop? Right, and that's essentially proactive approach. Don't wait for the problem to happen. Think about what problems can happen. If you're running a benchmark and you say like, if we get more users, we will need more memory. Get more memory now. Don't wait for it to fail and be like, we needed more memory. So be proactive and check stuff in advance. Okay, so that's it for today. So the next time, we have 2 more topics to discuss before we finish with this class. Those should be this addressing data issues and some future approaches to big data and so on that we will talk about, that I will try to illustrate. So that's essentially it for today. If there are any questions, feel free to ask me in chat or raise your hand. If not, you have my email. I will, while I'm waiting to see if anyone asks something, I will just write it down. But it seems there is no questions. Okay, so thank you very much, and that's it for today. So thank you, and see you. I think our next class is tomorrow, and that will be our final class. So thank you and goodbye.
Thank you. Goodbye.